Hi everyone, and welcome to today's webinar, which is Better Geotechnical Analysis and Design with LimitState GEO. I'm your host, Tom Pritchard. I'm joined today by Professor Colin Smith, who is the LimitState GEO Product Manager. He's going to be telling you a little bit about how LimitState GEO can be used to smooth the workflow and improve your geotechnical analysis and design. You'll also find out a little bit about the technology behind LimitState GEO and see how it's applicable to a wide range of different situations. Today's webinar is due to last about 30 minutes, and there will be some time at the end for questions, which you can post at any time in the webinar interface. We do try to get around to as many of the questions as we can during the webinar itself, but obviously if we don't have time, then we will try and follow up as soon as we can afterwards via email. With that in mind, if you do have any questions that the webinar prompts, then you can email us at any time on info@limitstate.com, and we will be more than happy to answer those questions for you. So without further delay, I'm going to pass you over to our speaker for today, who is Professor Colin Smith.
Thank you for that introduction, Tom. So just to whet your appetite, we'll kick off with a slide showing a selection of problem types that can be solved by the LimitState GEO software. So as you can see, the software has been designed to identify the critical collapse mechanism for any problem type in the form of a slip line mechanism. Now, in terms of the specific content of today's webinar, we'll be looking at the types of problems the software can solve, how it works, and the benefits the software can bring the engineer. And as this is a short presentation, the main aim is just to give you a flavor of what the software can do. There won't be time to get into the details of all the software functionality. However, as Tom said, there'll be time at the end for questions. So we'll start off with introductory example, looking at a slope stability problem, looking at the regrading of a slope adapted from a real case study. In this problem, there is a thin, weak layer of soil that's indicated in yellow in the diagram. And we could do a basic solution, trying to do a hand calculation using perhaps method of slices. But with that weak layer in place, the solution is going to be potentially much more complex. Now, if we analyze the problem first, assuming that there is no weak layer, with the software, we get this particular sliding mechanism for long-term analysis. And that is something that we could have analyzed using, for example, a slip circle or method of slices type analysis. And we probably would have got a pretty decent answer for that, assuming a slip circle. However, for more complex stratifications, the margin of error can increase. And of course, there's inherent variations between the different methods, for example, Bishop, Morganson, Price, etc. So this is where the LimitState GEO software comes into its own. Instead of making assumptions about the nature of the slip surface, it adopts rigorous plasticity theory that can identify any failure mechanism geometry. And in particular, this is going to be needed for the case where the weak layer is modeled. So here's the problem with a weak layer, and that's the failure mechanism that the software identifies. So that would be hard to model with a slip circle, and some non-circular methods can be a bit hit and miss in these cases. This particular mechanism is more critical in the previous case, where we didn't model the weak layer. Now, at this stage, I haven't said anything about the quantitative output of the software, and we'll cover this a little bit later in the presentation. So following on from that brief summary introduction, just say a little bit about challenge with traditional analysis methods. So essentially, things like method of slices require significant assumptions about the failure mechanism, you're assuming a circular slip surface, or maybe if it's a wedge analysis, a 2 or 3 wedge mechanism. And those are commonly simplifications in order to make the problem tractable. And other simplifications or assumptions are, what are the interslice forces when using the method of slices? If you're going to do it by hand, of course, that can be slow. Methods like the traditional approaches, most of them have been automated now, which speeds it up. And if you go to the other end of the scale using finite element analysis, then that can often require expert knowledge of the software and the technique itself. So what do engineers need from their software? Well, essentially, you need to reliably identify the critical failure mechanism, irrespective of form. of software that's simple and to understand and use, fast to set up and solve, and it gives useful output that's easy to interpret. And we would argue that LimitState Geo provides all of these. So how does it do that? Well, underpinning the software is the Discontinuity Layout Optimisation method, which provides rigorous upper bound plasticity solutions. These are rapid and direct ways of analysing the collapse state. The method came out of a EPSRC funded research project carried out at the University of Sheffield, and the key publication was in the Proceedings of the Royal Society in 2007. And we can describe that fairly easily. So this is a very brief overview of how the method works. We start off with a domain here as a rectangular block of soil. We've got a load on the top and supports to the left and to the base. We then populate the domain with a set of nodes. It's not a finite element method. We adopt a set of nodes. Here we've got a 4x3 array, that's 12 nodes. And we connect every node to every other node with a potential slip line. And then we use optimization to pick out of that set of slip lines. And in this case, we've got 12 times 11 over 2, 66 possible slip lines. Out of that, we can use optimization to find those slip lines that give us the critical failure mechanism, or the one that dissipates the least energy at collapse. So that selects out 6 of those slip lines to give us this particular mechanism. Now, in the main software, we don't use 12 nodes. We could be using 1,000, 2,000, 4,000 nodes and millions upon millions of potential slip lines. And again, the software can quite rapidly pick out the critical mechanism from those particular problems. So that gives us a robust, reliable, and accurate tool for identifying critical collapse mechanisms, irrespective of form. So one illustration here is a prenatal punch. This is a footing on a cohesive soil. We know the answer is 2 plus pi from textbooks, and the software can get there within less than a second and within 1% of the exact solution. And you can see in this animation that we first produce our set of nodes. The software then places the critical slip lines connecting those nodes. And then what it does is, once it's found the critical mechanism, it stitches those lines together in it, as it were, to form rigid blocks, and then those can be animated to aid interpretation. And one of the other advantages of the software is that it's inherently able to identify singularities in the solution. So at the corners of these blocks, you've got a lot of slip lines meeting at a point. This is a common feature of collapse ultimate limit state analysis. And it's something that can be harder to identify in, for example, finite element methods, which may require special meshing to do so. So, what are the benefits of using LimitState Geo? We'd hope to show you that it produces more accurate results, better designs, better understanding of the problem, can save you time, and give you cost savings. And we'll kind of illustrate that through the example of a stem wall construction. So our problem is that we have an embankment, an existing embankment, which we need to widen. The soil properties of the existing embankment, angles of friction 27 degrees, unit weight 18. And we're going to construct a stem wall and then backfill inside that with stronger material. And that will then allow us to take some additional loading, which might be for a road or a railway. If we want to design the wall or understand the problem, we could do some conventional analysis. So one possibility, and this is sort of classical limit equilibrium approach, is to use a Rankine analysis with a virtual back. Think about trying to calculate what the earth pressures would be on that. However, that is complicated by the fact we have varied surface loads, and we also have an inclined soil interface in there, which may affect the lateral earth pressures. Alternatively, we could use a Coulomb wedge analysis, try various wedge angles to give us the critical wedge for that situation. And again, that will take account of those surface loads a little bit better, but again, it's using just a single wedge. So we might miss the critical failure mechanism. So let's see how we can analyze this in LimitState GEO. So we'll start with a DXF import of the initial design and go from there. So I'm just going to pull the software over. So this is the standard interface. I'll describe some of the functionality as we go along, but we've got a number of menu bar items, buttons, and so on. What I'm going to do is start off by importing a geometry. So this is our DXF file. I'm just going to click OK to all of these settings. And when it imports, it produces construction lines. I'm just going to take those out for simplicity. So that gives us a bare bones of the problem geometry. We now need to add some material properties, boundary conditions, and loading. Now, initially, we might not have a detailed site investigation, but might want to carry out a scoping study based on general indication of soil type. And the software has built-in common materials. These appear on the left, what we call the Materials Explorer, and we've got a range of materials with sort of typical properties. So I'm just going to grab a few of those. So we could just click on one up here, very stiff clay. We can drag and drop that wherever we want. So I'm going to put that one at the base. And I'm just going to put a firm clay in for the rest of the soil in this problem. I'm going to use concrete here for the wall. And then I'm going to add a load. So here, I can click on a boundary. And anything I click on in the window here, its properties appear on the right in what we call the property editor. And here I can define some loads. So I can click here and access the variable loads. They're set at 0 at the moment. I'm going to set that to 10. And that load appears on the model. I could then try and run that. To solve the problem, we press this green button up here. Flags up an error. I've applied a support. So this thing is just floating in midair. I need to apply boundary conditions. So I'm going to set that to fixed. I can zoom in using the mouse quite easily. Click on that boundary. Click on that boundary. Their properties appear in the property editor. Again, I will set those to fixed. And on the right-hand side, again, I can zoom in, select one or more items, set those to fixed. So now I've got the problem as is, and I can click solve. And the problem applies the nodes to the system and then identifies all the critical slip lines. So there's our mechanism of failure. It's usually automatically animated. I can click this button again just to see the animation again. So it's a kind of broad, sort of bearing capacity failure under the load, leading to sliding of that and sinking of the wall in this particular case. Now that's got lots of wedges in it, so it's going to be more precise than just a single wedge analysis. And in terms of the quantitative output, we get an answer what's called an adequacy factor of 17.54. Just to explain what it is, we can click on the hyperlink here and it'll pop up and tell us what it's done. So when we're using ultimate limit state software, such as LimitState GEO, everything we design should be stable. So in order to get it collapse, we have to do one of two things. One is either increase a load in the system until it collapses, or alternatively reduce the strength of the system until it collapses. So in this case, what we've done is asked the software, how much bigger does this load on the surface? And this is on boundary 23. If I click on that, it will be highlighted up there. We set it at a value of 10. How much bigger does it have to be to cause collapse? For this particular problem, for an undrained analysis in these clay soils, we have to make it 17 times bigger to get to collapse. So it then has to have a load of 175. So we've got a very large margin of safety in this particular case. So hopefully that's given you a brief illustration of how we can import a model and quickly add boundary conditions and materials. What I'm going to do is open a pre-prepared model here, which has all the properties in that I showed on the PowerPoint slide. So let's just have a look at those. We've got the granular fill here. Again, the properties appear on the right, and we've got an angle of friction of 34 degrees, unit weight of 18. The existing embankment, again, its properties appear here. Angle of friction of 27, weight of 18. I can also just note that we can set not just properties of blocks of soil, but on interfaces. So on the base of the wall here, I've got an interface between the concrete wall and the underlying soil. And that I've set to be what we call a derived material, such that it has 3/4 or 0.75 of the properties, 3/4 of the properties of its parent material, which is the underlying granular fill. So that's automatically calculated by the software, and if the parent material properties change, then that one changes simultaneously. So let me just go back to the full image. Normally, we're going to want to analyze these problems using partial factors, Eurocode factors. So what we can do in the software is, using a scenario manager, we can get the software to automatically apply partial factors. In this case, we've picked built-in factors for design approach 1 combination 2. So we have a factor of 1.3 on variable actions, unfavorable actions, and the main thing is we're factoring down the soil strengths. And for a scenario, we can switch between short and long-term analysis, either using undrained or drained parameters. So we've got this set up for design approach 1 combination 2. This is most likely to be critical. We could check the design with this, and then we could check it under design approach 1 combination 1. So we'll run the problem and see what happens. So we click solve. So we get a mechanism which involves sliding down the interface between the existing embankment and the new fill. The wall is sliding, but also sinking slightly, and we get an adequacy factor on our load of 0.73. If it's less than 1, generally that means it's unsafe or doesn't comply with the code. If it's bigger than 1, it does comply. And if we click on that, what it's telling us is that those values that we've applied on the surface of the loads, they've been factored up by 1.3 according to the code, but then they need to be factored down by multiplying by 0.73 in order to give a value that would just put this system on the point of collapse. So in its present state, this thing is not stable. Now that's a factor of safety on load. We can also produce factors of safety on strength. So if I click factor strength mode here, we can switch from one to the other. It takes a little bit longer to analyze, but the software will identify the factor of safety on the soil strength to cause collapse in this particular system. So it's coming out with a value of 0.97. Generally, these factors are going to be different to factors on load. And what it's saying is our design values of material properties, they're almost strong enough, but actually we need to divide them by 0.97 to get to a point that we're just going to be on the point of collapse. So again, it's below 1, it doesn't comply. So I'll switch back to factor, so unlock the problem, switch back to factor load. So what can we do to stabilize this problem? We've got a whole range of choices. I'll only go through a few of them here. One is we could add a bit of fill in front of the wall. So I'm just going to raise this up to this level. Small amount of extra fill there just to try and suppress that failure there. And if we solve, it changes the failure mode slightly, makes the wall slide instead of sink and slide, and the adequacy factor has now gone above 1. It's a bit of a change, but that's because we've applied it to the surface loads. There is, of course, a lot of dead weight of soil behind the wall, pushing that wall as well. So that's helped. And if we've got an analysis that we like, we can look at a report. So the software will generate a report. If I click here, report, just say yes to that. And it gives us a full image of the failure mechanism, the partial factor set used, whole set of data about the boundaries and so on, material properties. So all the parameters that you need. And for simple problems, it will also give you 3-body diagrams of all those wedges if you wanted to check those by hand. So we have a satisfactory solution here, but with climate change and so on, what about the risk of flooding, for example? So we can look at that. If I click on this symbol here, I can draw in a water table. So I'll put it about here. So let's assume we've got a water table has risen. What does that do to our problem? So I click solve. That, of course, is going to change the effective stresses below the water table, and that has dropped our adequacy back down below 1. So if we have a flooding scenario, this is not going to be satisfactory. So again, we need to think, what could we do to try and address that? And there's a range of things we could do. We could add more fill in front of the wall. We could change the backfill geometry or its strength. I'm just going to look at the effect of adding some reinforcement. So as we're putting the backfill behind the wall, we could choose, for example, to add a layer of reinforcement. So I'm just going to draw in a horizontal layer here. And then I've got a material here called a geotextile that models a geotextile or soil reinforcement. I haven't got time to go into the details of all of that, but that's putting that in there. And if I click solve, we'll see what that does. So hasn't modified the mechanism much, but it has added strength and it's put our adequacy back up above 1. So that is a potential option that we could look at in more detail. So I've gone through all this fairly quickly, but hopefully you can see the scope of the software to give us a good understanding of the problem and the options open to us and the sensitivity of design to certain parameters. So that's going to brings us pretty close to the end of this short webinar. So just to summarize, hopefully you've seen that using the software, workflow is straightforward from geometry import to reporting. It's got a very intuitive user interface, puts you in control. You can solve with one mouse click, and it's easy to handle partial factor application. It's quite interactive. It solves quickly, so you can use it to answer what-if type questions, and empowers you to basically get a better feel for the problem. And just one piece of software can solve any ultimate limit state problem type. So there's no need to impose idealizations or correction factors for non-standard geometries, and no need to learn how to use many different programs or methods. And as I said, it can solve any ULS problem type. We just put a couple of other illustrations here, reinforced wall or a working platform. But you can model gabions, retaining structures, 1D and 2D earth reinforcement, and a whole range of other problems. So that brings us to the end of the presentation, and over to you for questions. So we'll just check the interface for questions. Okay, so we've got a question about how do we model yielding based on different nonlinear constitutive models? So as I said earlier on, DLO is based on linear optimization. So the core software essentially works, uses a more Coulomb model for modeling cohesion and friction, which is a linear model. You can model a nonlinear yield surface as long as it's convex. And the way you would do that in this particular software is simply bracket the nonlinear curved yield surface using a set of straight lines. So basically you're putting a set of tangents to that, and the more tangents you use, the closer you get to the curve that you want to work with. So if I go back to the software and we look at a material model, we have a C dash and a phi dashed. And what I can do is create, for example, duplicate that material. So I've got a copy there. If I wanted, I could have a different C dashed, a different phi dashed. I'm just going to change the color on that. Make it a slightly different hue. And then we can add that. So what we get is a combined material with effectively two yield surfaces, and the software will always take the lowest part of the yield surface. So you can basically bracket a curved surface with a set of tangent lines, and that's how one can model a non-linear model, and that will work perfectly well with the optimization within the software. Got a question about importing geometry using XY tabulated data. At present, we don't have that facility. The import is built on importing a DXF model of the geometry. Got a question. Can I say a little bit more about the geotextile modeling? So here, if I click on the geotextile here, geotextiles and soil reinforcement are essentially modeled using what we call an engineered element in the software. And there's a number of parameters which I don't really have time to go into, but essentially you can model a one-dimensional object in the software that has a rupture strength or a tensile strength. It has a compressive strength. If you want to model sheet pile walls, you can ascribe a moment of resistance to that. If I just drag that across, you can see these parameters better. So these all define the properties of the actual element. So that allows us to model a whole range of things from geotextiles to soil nails to sheet pile walls. And then we have some additional factors here, which are relevant only to one-dimensional reinforcement like soil nails, which allow us to put in pull-out factors and so on. So those could go in the model, and they're essentially modeled in exactly the same way as reinforcement is treated in conventional sort of wedge analysis methods that are conventionally used for reinforcement. There isn't time to go any more detail in that today, but we do have webinars which address the reinforcement question in more detail. Okay, I think that covers all the questions we've had so far. So I'm going to pass back to Tom just to wrap up. So thank you very much for listening.
So thanks, Colin, and thanks to everybody for joining today. We're now at the end of the webinar, and we do hope that you found it informative. As we mentioned at the start, if you do have any questions that arise after the end of the webinar, then please feel free to send them to info@LimitState.com, and we will be more than happy to answer them for you. We're going to make a recording of this webinar available on our YouTube channel over the next few days, and anybody who registered for the webinar will get an email to tell them when that's available. You might also be interested to know that we'll be having other webinars throughout the year, some of which will, as Colin mentioned, be dealing with more advanced and specific parts of the software. So please do look out for those. We'll be sending out email and social media notifications in advance of those. So lastly, just want to thank everybody again for joining us today, and we do hope that you will be able to join us on one of our future webinars. Thanks and bye.